Now, what we've done formally is demonstrate that U exists. But every step of the proof that we've employed also leads to the conclusion that U is unique. Okay, the way we've defined it, especially the fact that we've chosen the positive eigenvalues for U, essentially means it demonstrates that U is also unique. It's easy to just go back through the steps and show that if you consider a different U with different eigenvalues and different eigenvectors, you will conclude that, well, those eigenvalues and vectors cannot be different. They have to be the same as the ones that we just got from C. Okay? Right? So essentially the same steps also imply that U is unique. Okay? If U is unique, U exists and U is unique, okay? What this implies then that if we have F equals RU, we can define an R which is equal to F U inverse. Okay? So there exists an R. Let's check if it's an orthogonal tensor. Well, R transpose R equals U inverse transpose F transpose F U inverse. Okay? And here we have this is R transpose and this is R. But let's carry the mathematics through. U inverse transpose. U is symmetric, therefore U inverse is also symmetric, therefore U inverse transpose is simply U inverse. U inverse, we have F transpose F, which is C, and on the right we have U inverse. But then C we know is U square. So we have U inverse, U square, U inverse, which is again the isotropic tensor, right? Because the U inverse essentially kills each U in the U square. So what have we just done? We've demonstrated that R exists. R can be defined as F U inverse. We've demonstrated that R transpose R equals the isotropic tensor. So what we've just demonstrated here is that yes, indeed there exists an R belonging to SO3. This symbol, by the way, the reversed E, it means there exists. Okay? So we've essentially concluded that our polar decomposition exists, our right polar decomposition exists, and is unique. Right? Okay. So those are the mathematical properties of our polar decomposition. What I'm going to do in the next couple of minutes is provide us with a physical interpretation. For the physical interpretation, let's go to our picture of the configurations, physical interpretation. Okay? We have our basis, we have the reference configuration, current configuration, sorry, omega sub t, yeah. Okay, and we have phi. Now, we are going to consider a little neighborhood of material here. Let's consider a point x here, okay? We know that that point goes to little x, okay? And that is done, we know that vectors around capital X, around the reference position, are mapped by the deformation gradient to vectors around little x. Now, since we can write f is equal to Ru, and we know that f acts on a vector, it implies that if we consider a little vector around this point, right, let's consider this vector. And as before, let's write it as epsilon m. Okay? We know that under the deformation, that vector maybe goes out here. Correct? Now, F acting on epsilon m is the same as R U acting on epsilon n. The effect of U, because it admits this idea of a polar decomposition involving the eigenvalues which are positive, okay, the effect of U is the following. What U is doing is to take a little neighborhood around our region here, okay, and I'm going to take a neighborhood with, I'm going to draw it as a rectangle for certain reasons here. The reason I've drawn it as a rectangle is because I want us to think of the edges of that rectangle as being aligned with the eigenvectors of U. I know I haven't drawn the eigenvectors as being the same, and I need to draw 3 of them. I'm just drawing 2 of them because I'm limited by the two-dimensional nature of this board. But anyhow, you get the idea, right? The first action of epsilon upon a neighborhood around X is to essentially only stretch out that neighborhood along the eigenvectors of U. So if we were to take this neighborhood out of our reference configuration and look at only the effect of U upon it, what we would see would be something like this. The effect of U is to take that neighborhood of ours, and I'll try to draw it with the same orientation, maybe this. It's taken that neighborhood and stretched it out along its eigenvectors. Okay? That eigenvector is n1, that eigenvector is n2. Okay? Now, an arbitrarily oriented vector such as epsilon m lying in that neighborhood could change its orientation if it is not aligned with the original eigenvectors, right? So that vector that I've drawn, epsilon m, could well end up having a different orientation, say this one. Okay? Under the effect of U. Okay, so this is U epsilon m. Okay, as you can see, the orientation is different. It's also been stretched out maybe a little. So let me just pull it out a little to the back to indicate that its length is a little different. Okay, importantly though, the sides of the rectangle have not changed their orientation because they were originally aligned with the eigenvectors of U. And those eigenvectors are undergoing pure stretches. The extent of the stretches are given by the eigenvalues of U. Okay, that would be lambda 1 applied to that original length of the rectangle, and that would be lambda 2 applied to the original width of the rectangle. And then R comes into the picture. Okay, unfortunately I've drawn this neighborhood too big to fit inside my current configuration, but nevertheless I'm going to draw it there. Okay, it's just the fact that my drawings are poor here. Essentially what R does is to take this purely stretched neighborhood and rotate it to some other orientation. Okay, so let's draw it here. I'll try to squeeze it inside here. That is what R has done to that neighborhood, right? It's simply rotated it without changing the lengths of its sides. Okay? This is the effect of the components of the polar decomposition upon a vector. Okay? So, U stretches neighborhoods around X. R rotates them. Okay? It is for this reason that the eigenvalues of U, the lambda I, are also called the principal stretches of f. Those are the directions which are purely stretched. Okay, the directions corresponding to the eigenvectors are purely stretched. Okay, lambda I are the principal stretches, and ni are the directions that are stretched by u. Other directions do undergo some rotation, as we demonstrated for our vector epsilon m. Okay? Okay, I should probably indicate that in the final picture we have epsilon m, which is u epsilon m, which has also been rotated now. So now this is r u epsilon m. Okay, we'll stop here for this segment.